before I get into solving some problems, let me go and share my screen. Are you seeing a WebAssign problem now on the screen? Hello?
Yeah.
Yes, we can see you.
All right. So I'm not going to give you a problem like this on the next exam. On the next exam, you'll have two problems, plus there'll be some problems too on Laplace transforms, but that we haven't talked about yet. But on the next exam, you can have a problem where you have to solve a power series about an ordinary point, which is what I did yesterday. We're going to talk more about today. And you'll also have a problem about solving a differential equation using power series about a regular singular point. So we're going to talk about, when you use the two different forms. But I'm not going to give you any problems on the, like on the ratio test to determine divergence and convergence on the exam. But I do want you to be able to do two problems that I have in the WebAssign, okay? And basically one of the two problems are right here. I'm showing you the two problems right now, and they're on Blackboard. These are the two problems, okay? So the only difference is you're gonna have different numbers, okay? You're gonna have different numbers. So just now, this is something you should have learned in calculus too. Just a quick review, one of the ways we could determine whether, what value of X this series here is going to converge is we could do the ratio test, right? So I'm showing you right here, this is the ratio test, right? We just put n plus 1, right? Wherever I have an n, I put n plus 1, and then you divide by n, right? And then you take the limit as n goes to infinity. So you can see in this case here, when we take the limit as n goes to infinity, right? This just becomes 1. So in this case here, it's just 5 times the absolute value of x has to be less than 1, right? For this series to converge, right? Because remember now, if it's less than 1, it converges. If it's greater than 1, if this turns out to be greater than 1, it's going to diverge, right? And if it's 1, it's inconclusive. All right, so that's the rules for the ratio test. So I want you to study this problem here. Now, with the ratio test, though, we also have to check the endpoints, right? So, for example, I put in 1/5 here, right? I put in 1/5. That's all I'm doing here. In place of x to the n, I'm putting in 1/5, right? And then this turns out to be 1 to the n. Now, this series diverges. Remember the p-test? The p-test tells us that that if I have 1 over n to the p, that it diverges if p is less than or equal to 1 and converges if p is equal to 1. So in other words, if this p was 1.2, this would converge, right? But the p is equal, the p here is just 1. So this series, so in other words, when I, right, for 1/5, right, for 1/5, the series is going to diverge. So we can't include 1/5. See, here they wanted to know the interval. But when you include minus 1/5, right, this now becomes an alternating series. And the rule when you have an alternating series in the limit, in other words, in the limit, if a sub n goes to 0, then the series converges, right? So, okay, so I want you to study this type of problem. The only difference is that, instead of having a 5 here, you may have a 7. All right, so, but I want you to understand this problem. All right, and like I said, I'm not going to, that's one of the reasons why I count the, I can't give everything on the exam, and so that's why we count the WebAssign is like one exam. Okay, so, but I'm helping you out here. Okay, and this is something you should have learned in calculus too. All right, and then there's another problem here too. Okay, similar problem. All right, so I want, once again, instead of having a 4 here and a 12 here, you may have something else. You could luck out and have what I have. Okay, so all right, so that's that. Let's see. Let me do something else here now. Now, I also have here a little review of power series, and I kind of talked about this, that, this is the Taylor series, and this is the McLaurin series. And this is what I did. I showed you that the sine is actually equal to, what I have here, right? This is sine. And that if you were to do the ratio test, if you do the ratio test on this, you'd find that, which makes sense, that this series converges from x is equal to minus infinity to plus infinity. Okay.
So we're just seeing your notes right now. We're not seeing this.
Okay, thank you. That's right. I forgot to put it. Thank you. Let's see. Okay. All right. So I just have some notes here on a review of power series. Okay. I want you to understand this stuff, but to solve the problems that are going to be on the exam, you really don't need to understand the Taylor series and the McLaurin series. But that's kind of where it comes from. Here I'm showing you where the where the series comes from. This is kind of like a proof of how you get from here to here, or why it's true. And so these, if you're going to continue in mathematics, there's more, but these are 3 power series you should commit to memory. What the cosine is, what the sine, what e to the x is, the inverse tangent. There's some others as well. Let's see. Yeah, here, for example, here I'm using the ratio test to show you that that this converges from this is e to the x. This should converge from minus infinity to plus infinity. Don't worry about this last page. This should be minus infinity. The e to the x converges from minus infinity to plus infinity. Oh, okay. Sorry. I'm looking down. I was looking. See what I was doing? It's correct. I was looking at this down here, thinking that this was the answer for e to the x. Here's the answer. So you see, e to the x converges from minus infinity to plus infinity, right? Which makes sense. E to the x is convergent. So here's the example of the ratio test, and we see we get minus infinity to plus infinity. Then the arctan, however, the arctan, this is only going to converge from -1 to +1, right? The arctan cannot be greater than 1. It can't be less than -1. It can't be greater than +1. Okay, so this is showing that the ratio test has given us the right result for e to the x and the arctan. Yeah, when I saw this down here, I wasn't looking at this, and I thought that this was e to the x. All right. So that's just a little bit on power series that you should have learned in calculus 2. Okay, so now let's talk about what we need to know for solving differential equations using power series. Okay, so I want to talk about what an ordinary point is and what a singular point is, and so if we have a differential equation that looks like this, with my glasses on, and you can follow along on my notes, but okay, so we have a differential equation that looks like this, right? I take this and I divide by x, right? That's all I'm doing here is I'm dividing this by x, right? So the x cancels out and I get this, okay? Now, it turns out that for this differential equation, I can assume a solution of this form, provided that x sub 0 is not equal to 0. In other words, the equation 1, if x of 0 is an ordinary point, okay, so if in this equation here, if this x of 0 is an ordinary point, all right, then we can assume a solution of this form. All right, let me I think the next example is going to explain it better. All right, so we need to know what an ordinary point is. All right, so So here's a second order differential equation, right? We've got the second order differential equation. The first thing to do is to put it in this form, right? In other words, if I have an x here, I'm going to divide everything through by x. So here I have some function of x in front of the y prime, and then some function of which I'm calling q in front of the y. And these could end up being constants, right? So in this case here, this is 1 over x, right? And the q is 1 over x, right? Just taking this case here, for this differential equation. So it turns out that 1, okay, 1 is what we call an ordinary point because this is defined, right? That's just what, this doesn't blow up, all right? So 1 is an ordinary point. 1 and q here, 1 is an ordinary point, okay? 0 is what we call a singular point, right? 0 is a singular point because if I put 0 in here, this becomes undefined, right? That's all you need to know. When I put 0 in here, this becomes undefined. So an ordinary point is a point where my p here, right? This function p and the function here q, and it could end up being a constant. If they're defined, then I have an ordinary point. If they're not defined, then I have a singular point. All right. So so it turns out for this equation here, right? For this differential equation here, right? We write it in this form, but for this differential equation here, I can assume a solution that looks like this, right? Because 1, right? 1 is an ordinary point. So I can assume a solution that looks like this. I can't assume a solution. For this differential equation, I cannot assume a solution that looks like this, okay? It will turn out that I can assume a solution though that looks like this, where this is n plus r. All right, so there's two things here that on an exam you'll get a problem where you're gonna end up assuming a solution like this. I'm always going to do it about 0. And then you'll have also a problem where you have to assume a solution like this. And this would be n, and then it's x minus n plus r, right? We'll get more into this, all right? So I hope you would. So I can't assume a solution to this differential equation of this form, right? Because it turns out that 0, right? 0 is not an ordinary point. I have to have ordinary points to assume this solution. All right, so let me remember the problem we did yesterday. Like, let me just skip ahead. Like this problem here, 0 is an ordinary point, right? This is one of the problems we did yesterday, right? It just happened to be a constant. So my p here is just 1, right? So 0 is an ordinary point. So when I have an ordinary point, I can assume a solution of this form. Now, also the other problem we did yesterday, this problem here, right? Once again, 0 is an ordinary point, right? 0 is an ordinary point, all right? So I can also assume a solution of of this form, because 0, I could put 0. 0 is good here, right? But let's see now. Now, if I take a look at this here, I'm dividing through by 0. So I cannot assume a solution for this differential equation, right? I can't assume a solution of the form I had before, but I can assume a solution of this form. We'll see why. I can assume a solution of this form, where this is n plus r. All right. So let's continue here. Okay. So so here's an example, right? So we consider this differential equation here. I divide through by x squared, right? I divide it, I have to get this in the form of like I had before. There's no P here, right? So this is not analytic, right? In other words, when I put 0 in here, it's not analytic, and therefore we can't assume a solution of this form. All right, let's skip a page. Maybe not. Okay. So 0 is a singular point. All right. Now, if I put 2 in here, though, if I put 2 in here, right? 2 is analytic. In other words, if I put 2 here, right, 2 is a good point, right? So if I want, I can assume a solution x minus 2 to the n, all right? I want you to understand this. You can assume a solution around the point 2, right? This is around the point 2. It's not minus 2 because it's x minus 0. So I can assume a solution around the point 2, but I can't assume a solution around the point 0, right? Because of this here, right? So actually, x of 0 is an ordinary point, all right? It's an ordinary point. Here's another example, right, where we have this differential equation. Now, in this case here, x of 0 is an ordinary point, right? In other words, if I wanted to solve this differential equation, I can assume a solution of this form, right? Because if I put 0 in here, that's okay. If I put 0 in here, that's okay. So I can assume a solution of this form. I can assume a solution if I wanted to put, if I wanted to assume a solution of this form, x plus or right? If I wanted to assume a solution of this or this, where x is plus or minus 1, it's not going to work. Okay, I can't do that. All right, because when I put a 1 in here or a minus 1 in here or a plus 1 in here, both of these become undefined. Right? So that's what we call singular points. So now we know the difference between an ordinary point and a singular point, right? And the easiest way to do it is, the easy way to think about it is that an ordinary point, it's not going to, we're not going to go to infinity, right? It's going to be defined. That a single point isn't going to be defined. Okay. All right. So now, though, we need to know there are actually two different types of singular points. We need to talk about a regular singular point and an irregular singular point. And it turns out when we have a regular singular point, then we'll be able to use this. If we have an irregular singular point, then we can't use power series as a method of solving the differential equation. Well, we can use power series as a method of solving the differential equation, but we can't, we need to have a regular singular point to use this form. All right, so now I need to talk about a regular single point, irregular single point. Okay, so as I said here, there are two types of single points. There's a regular single point and an irregular single point. Okay, now when we have a regular single point, we can assume a solution. All right, so I need to define what a regular single point is, but first, that when we have a regular single point, we can assume a solution to our differential equation, not just n, but we got n plus r. All right. So the whole goal here is for you, I want you to understand when you use x to the n and when you use x to the n plus r. All right. Okay. So here's how it works now. All right. So and I'm using the same notation that's in your book. So first of all, we write the differential equation in this form, okay? Where if I had an x squared here, I have to divide everything through by x squared, okay? And then what we do is we define what we call a little p of x and a little q of x, where little p of x is equal to x minus x0, where x0 is the point that we want to expand our power series about. Now, once again, all the problems I'm going to give you is x0 is equal to 0, because that's what's the most important point. All right. Normally, we want to know the power series about 0. We want to start at 0. But anyway, the more general is we got x minus x0, okay? Now, it turns out if both P and Q, now notice here we got the square. This is squared. Here it's not squared, all right? So for the Q, it's squared. Here it's not squared. So it turns out if both little p and little q, well, once again, little p, we're just multiplying this times big P, and little q, we're multiplying this times big Q, that if both the little p and the little q, right, lowercase, I should say, are analytic, does not become infinite, then x of 0 then is what we call a regular single point. So if P and Q are not analytic at x of 0, then x of 0 is an irregular single point. So the cases that you're going to have is that, we're going to have x and P of x, let's say. You multiply the x times the P of x, the big P of x. And if this turns out, after you multiply it by x, if this turns out to be analytic, or we're not dividing by 0, then you can assume a solution of this form. All right. And this is known as the method of Fabini's. Okay, let's see. Let's do some examples here. Okay. So once again, if both P and Q are analytic, so here's kind of like a summary. So if both P and Q are analytic at x equals 0, right? We call x of 0 an ordinary point, and we can assume a solution of this form. Now, once again, the problems I'm going to give you are going to be like this. Okay, we're going to assume all the problems I gave you, both in the Weber sign and on any exam, will be about the point x equals 0. But I just want you to understand, though, you could expand about another point as well. Okay, but if you do one, you can do the other. Okay, now a regular singular point, in order to test, if we have a regular single point, we just multiply it by x minus x0. Or, if we're doing, it'll just be this, right? If we're doing it about 0, and this will be, this will be little p. If we're doing it about 0, and this is x squared. Okay, so if both this little p and little q are analytic, so basically what we're doing is we're reducing, we have a certain, if this is x here, right? This is 1 over x. I multiply by x, that makes this a regular single point. If this is my a regular single point, okay? So then we can assume a solution of this form, if x of 0 is equal to 0, which is what we're going to be doing. All right, so let's do some examples. So, all right. So in this case here, x of 0 is a regular point or irregular. What is this? Is this a regular point or irregular singular point? Well, let's see. Okay, so when we look at this, right? Well, first of all, I have to get it in the right form, right? So the first thing I do is I divide this equation by x minus 1 squared, right? Now I want to know if 1 is a singular point, right? So this is my P of x, right? This is my P of x. This is my Q of x. So now I'm going to multiply it by x minus 1. I want to know if 1's a singular point, right? You multiply it by x minus 1. And this is not analytic, right? Because what happens here is that this cancels with this, and I still have an x minus 1. So this is going to blow up, right? At x equals 1, this becomes infinite, all right? So now this one here, this is analytic, all right? But both the P of x and the Q of x, right, have to be analytic. In other words, they can't blow up. So both the little p of q, right? So both the p, the lowercase p and the lowercase q must be analytic to be a regular single point. So x of 0 is an irregular single point. So that means that if I wanted to, I can't assume a solution of this form I can't assume this, okay? Because I got a problem here. I got a problem here with x is equal to 1, right? This is okay, right? Because both of these cancel out. So this is analytic, but here this is not. All right. Okay, so here's another example. Is x sub 0 a regular or irregular single point? But once again, now these are more like the type of problems. You know, the problems, like I said, I'm going to give you, it's going to be expanding about x equals to 0. All right. But you may have problems like this on the web assignment where you have to determine whether the points are regular or irregular single points. Okay. So okay. So in this case here, if I divide everything through by x, here I get an x and here I get an x. Now I just multiply. I want to do this about the point at x equals 0. So I just multiply this by x, right? Because remember the rule. Right? I'm just multiplying because now my x of 0 here, this is 0, right? This is 0, this is 0. So I'm just multiplying it by x. Okay, so so now for this differential equation, okay, this is analytic, right? If I multiply this by x, I get 1 over x, I get x times 1 over x is 1, so that's analytic. When I multiply this by x squared, I'm getting x. X is also analytic. You know, I'm not dividing by 0. All right. So since P of Q and X of Q are both analytic, okay, the real definition of analytic is that these functions can be written in terms of the power series. But don't worry about that. As far as we're concerned, we're not dividing by 0. Okay. Okay, so for this differential equation here, I can assume a form like this. All right. So this is what I want you to understand. I want you to understand that for this differential equation, I can assume a form like this, but I also want you to understand I can't assume a form like this. Right? Because x is not an ordinary point, right? Excuse me, 0 is not an ordinary point, right? 0 is a singular point, but it turns out it's a regular singular point. So it's a regular singular point, I could use this, right? Only when it's a regular singular point, I could use this. But if it's an irregular single point, then I can't expand it about that point. I got to expand it about a different point, right? So the key thing is that once you understand that, once again, I'm repeating that the differential equation looks like this, and if I'm expanding about 0, I have to use this form, and I can't use this form, right? I can't use this. I have to use this. Now I have to show you we haven't solved. I'm going to solve a differential equation today. Hopefully, I'm going to get to that where it's of this form. Okay. All right. So this is what we did yesterday. I solved this differential equation, and here you see there's no problem, right? I'm not dividing through by, you know, I don't have an x any place. I don't have my p of x in this case. Well, my p of x in this case is 0, right? And my q of x is 1. So I don't have a problem here. So I can assume a solution of this form. Right? I can assume a solution of this form, and that's what we did yesterday. All right. And this is the other problem we did yesterday, where I got an x here, right? And here it is nothing, right? So so x equals 0 would be an ordinary point. So for this problem here, I can also assume a solution of this form. All right. I can assume a solution of this form. I don't have a problem. Okay. Okay. Oh, now we can get into radius convergence. Now, you will have some problems like this. let's see. If so if I have a differential equation that looks like this, okay, we can find two linear independent solutions of the form where both solutions are of this form here, right? Where this turns out to be an ordinary point, right? Once again, is that whatever this happens to be, whatever I'm experiencing this about, it's not a problem for this for the P of X or the Q of X, right? I can assume in this form. Now, we do this without proof in your book, but the power series converges at least on some interval defined by x minus x0 that's less than r, where r is the distance from x sub 0 to the closest singular point. Okay, so so let's see, what does that mean? Okay, so here's the differential equation. Okay, and we want to find the radius of convergence. All right, so see, it's a little bit different than for the power series. You know, we can also find the radius of convergence by using the ratio test, right? But here now we're doing another method when we have the differential equation to find the radius of convergence. Okay, and we're getting that the radius of convergence is at least. In other words, it could even be greater, but the radius of convergence is at least. So here's what we do. So first of all, I have this differential equation, right? And I put it in the right form. So in other words, so as all as I did here was divide through, right? So in other words, let's see. See something happened here. What happened? Okay. So let's see. All right. So as all as I did here, which is x squared minus 2x plus 5 plus x. So that's my differential equation. So I have to get it in the form. I have to get it in this form, right? So as all as I do here is I divide by this, right? Okay, so that's all I did here is I divided through by this to get it in this form. Okay. So okay. So our rule now, let me go back, is that that we're gonna get a convergent series at some interval defined by this, where r is the distance from x sub 0, right, to the closest singular point. Okay, to the closest singular point. So let's see. So and this even works for imaginary. So let's say we want to find two linear independent solutions about the point x sub 0 is equal to 0. All right. So so we want to find that distance, right? We're told that the radius of convergence is at least the distance from x sub 0 to the nearest singular point. So where is the nearest singular point? Well, the nearest singular point is when the when this is equal to 0, right? When this is equal to 0, right? When these are equal to 0, that's going to be the nearest singular point, right? So I use the quadratic equation to find when this is going to be equal to 0, right? And so I get in this case here we get I is equal to plus or minus 2I, right? Now the point x is equal to 0 is here, right? And so this is my point, right? My point is if I do it in the in the imaginary plane, right, where this is I can call this yeah, this would be 2i, right? And this would be x, all right? So this would be y, all right? The distance here, right? This point, right? This point is 1 comma 2i, right? This point's 1 comma 2i, all right? So this distance is the square root of 5. See, that's all we're doing, okay? It looks more complicated than what it is. It sounds a lot more complicated than what it is. But it's all we're doing is we're finding, once again, we're finding the nearest singular point, and the singular point is going to be where this is equal to 0. All right. So then I use the quadratic equation to solve this for 0. Right. And the point I get is I'm getting a point of y of I of 1 plus or minus 2i. So that point is right here, right? That point, if I draw this as this is the imaginary axis and this is the real axis, right? Then this is 1, right? This is the point 1, 2i. This distance here then is just the square root of 5, right? So that tells me that my I'm guaranteed to have a radius of convergence of at least the square root of 5. That's all we're saying here. Okay, I think there's another problem. Okay, yeah, so here's another problem. All right. Okay, now this time here, we wanted to find 2 linear independent solutions about the point, but not 0 this time. This time it's minus 1. All right. So it's the same problem, but find 2 linear independent solutions about the point minus 1. And so we want to find the radius of convergence is at least y. Well, once again, I just set this equal to 0, right? Because that's going to tell me where my nearest, when it's equal to 0, that's going to tell me where I have a singular point, okay? So I use the quadratic equation, and it's the same problem, right? I get, I'm taking the same thing here now. It's 1 plus or minus 2i, right? 1 plus or minus 2i. But now, before I was interested in x of 0 is equal to 0. So this was my point. So I calculated this distance, right? Now, for this problem here, it's about the point x of 0 is equal to minus 1. So now I'm looking at this distance, right? This is minus 1. So you see this distance now with the square root of 2 over 2. So I'm guaranteed that my radius of convergence is at least the square root of 2 times 2, right? All right, this distance here is 1, and this distance here is 2, right? And then you use the Pythagorean theorem to get this distance. All right, right. This is 2. This is 2. Right. So r is equal to 2 squared plus 2 squared. All right. So and I could I could have a solution of this. I could use this, right, about this point here, right, because this is this would be this would be this is an ordinary point. Okay. All right. All of that. Let's see. Okay, so now so once again, basically we're gonna have you're gonna have 2 types of problems on the next exam. Hope I don't sound like a broken record. Where you're gonna have one problem where you're gonna use this form, and you have one problem where you're gonna use this form. Okay, and there'll also be problems on Laplace transforms. Let me just want to find something first. How are we doing on time? Give me a second here. the overall method is, it's going to be basically the same as what we did the last time. Okay, let's see something here. I want to look for something. Let's skip. Okay. All right. Let me get some paper. These problems are a little long. Hopefully I can finish. Let's see what time is it. Okay, so so we talked about a lot of different things, but it's easier than, okay. So I want to solve this differential equation here. I want to use power series to solve this differential equation. Okay. So the key thing, what I want you to realize is that to solve this differential equation, right? If I write it like this, let's get it in the form. Okay. So that's all I did is I divided everything through by 3x and I wrote it like this. Now, this is what I want you to understand. We talked about a lot of different things, but what I want to make sure you understand is that for this differential equation, I cannot assume this. Right? This is what you need to understand. I can't assume this. Right? I can't assume about, because I'll be expanding about x is equal to 0, right? When I assume this form, I'm expanding about x is equal to 0. This is not a, it's got to be an ordinary point, right? This is a singular point, right? But it turns out it's a regular singular point, okay? It's a regular singular point. So, so because this is a regular singular point, okay, I can assume a solution of this form. Right? Well, that's R, that's some value R. Okay. So that's the key thing, is that I'm dividing through by 0 here. And so because I'm dividing through by 0, I can't assume a solution of this form. However, you know, we're not going to do problems like this, but just so you understand, it's more should be about learning, but I can assume if I want to, I can assume a solution. I can't assume a solution about x is equal to 0, but I can assume a solution about x is equal to 1. Okay, but many times we want to go through 0, and maybe our radius of convergence isn't big enough. All right, so we rather assume a solution of this form than assume a solution of this form about a different point, right? So I hope you understand that you can assume a solution about -1. 1, this would be 1. You'd be assuming a solution about 1. But you can't assume this, because this would be about 0, and we got a problem here with 0. All right. And if this was x squared, suppose this was x squared, and this was x squared, I'd have a problem. I couldn't do this either. Right? Because when I multiply this by x, right, I still get a 1 over x, right? So if I had a 3x squared here, I couldn't assume about 0, right? Once you understand that as well, I couldn't assume about 0, all right? Because I still have a power of x at the bottom here. Okay, all right. So, all right, so let me, all right, so now we're going to assume a solution of this form, all right? Let me actually start on a different sheet of paper. So Yeah. Okay, so now let's see, how do we solve this? Okay, so I'm going to assume a solution of this form. Okay, you can assume a solution of this form. So I got this n plus r, okay? Okay. All right, so we're going to take the derivative of this and plug it into the equation. And the process is going to be a lot like what we did yesterday. But this is a double prime here. Okay, there's a few differences. So first of all, when I take the derivative of this, right? Take the first derivative. This is going to be c. Let's see how long. Be c to the n plus r over x x to the n plus r minus 1. Now remember, yesterday when we assumed the form, we started it from 1, right? Because when n is 0, but I can't, in this case here, I have to start it from 0 because I don't know what r is going to turn out to be, right? I don't know what r is going to turn out to be. So so when you take the derivative, you're not going to increase the index, right? Remember, like yesterday, we did this. And then we did this. Right? I could start this from 1 because when n is 0, this is going to be 0, but I can't do that now. Right? Hopefully everybody understands that. So I'm going to start this from 0. Let's see. Okay. Any questions so far? So that's all I did here. I'm assuming this is the solution. I take the derivative, take the second derivative. Now I'm just going to plug it into this equation here, right? I'm just going to plug it into the equation. And let's see. Now, here I got a 3x, right? I wonder if I should, well, let me not skip a step. I'll put, then I have a plus. I'm just putting them into the differential equation. We're going to be able to fit it. And then minus. Okay. Let's see. So all I did was put everything into the into my differential equation. Okay, let's see here. All right. Make sure I don't make a careless mistake. Okay, here I got a 3x, right? And here I got a so I'm going to bring this x in here. In other words, I'm going to write this. I was going to skip this step. I'm going to write this as this, like this. And put the 3 here. I was going to skip this step, but let me. Okay, here I got an n plus r minus 2, right? So now I got an n plus r minus 1 because I got this x here. I'm bringing the x in here, right? I'm bringing the x in here, so that's going to make this minus 2. Let's when I bring the x in, this will become -1. All right, so now I'm just recopying it. I was going to skip that step, but try to write a little neater. Okay. All right, now what? Okay, well, once again, here I got a n plus r minus -1. Here I got an n plus r minus 1. Here I got a n plus r. Okay, so let's see. So once again, I'm going to let I'm going to let k, just like we did before. I'm going to let k equal to n minus 1. Okay, we'll let k equal to n minus 1. So therefore, yeah. So okay. So therefore, n is going to be equal to k. Excuse me. N is going to be equal to n is equal to k minus 1. So when n is equal to 0, let's do this here. When n is equal to 0, k is going to be equal to -1. Right? When n is equal to 0, k is going to be equal to n minus 1. And n, okay, and n is going to be equal to k plus 1, right? N is going to be equal to k plus 1, right? All right, see here I want you to make sure, let me know if I go off the page. I want to get the n plus r, and here I got a n minus 1, right? So just like we did the last time. And so I'm going to do the same thing here, right? So in other words, I'm going to have k is equal to n minus 1. And then when n is equal to 0, k is going to be equal to -1. And then when n be k plus 1. Okay, and here I'm just going to let n is equal to k. All right, so let's see what happens. So let's see what happens now. Okay, I just want to check here. Okay, so yeah, so n is equal to, okay, so all right. So now I'm going to have summation n. Am I off the page? I'm good. Okay. So when n is equal to 0, so this is going to be k goes to -1. This is going to be k equals -1, right? When n is equal to 0, k is equal to -1 based on this substitution, right? So this is 3, and then this is n. So this is going to be k plus 1, right? This is k plus 1 now. Now here now, this is going to be a k plus 1, right? I'm replacing the n with a k plus 1 plus r. Now this is going to be a k plus 1, but I got a -1 here. So this is just going to be k plus r, right? This is k plus 1 -1, so this is k plus r. And now I got x to the, this is just going to be x to the k plus r, right? That's the way I set this up, right? Now the next one, once again, this is starting from n is equal to 0. So this is going to be k is equal to -1 to infinity. Now this here is going to be c to the k plus 1, right? Now here I got n. So n is going to be k plus 1, right? K plus 1 plus r. Let me put the plus r. Plus r. And now I got a minus. And here I'm just going to make k equals 0. I'm just substituting in, just like we did the last time. And this is going to be k plus r equals 0. Sorry about that, but this is k plus r here. right? This is, let's see, this is K plus R. All right. Should have moved this more over. Okay. All right, so what's next? All right, let me just copy it over, Nita.
Professor,
Yes.
after for the second summation, isn't there supposed to be a x k plus r missing?
This semester.
Yes.
Oh, X to the right. Thank you. This is N. Yeah, this is K plus R, right? K plus R. Right. Yeah, let me write it over, Nita. I ran out of room. Yeah. Good. So let me just copy it over. K plus R. Let me get X to the K plus R plus summation now. K goes from -1 to infinity of C to the K plus 1. And then this is K plus 1 plus R. And then we got X to the K plus R. And then, oh, this is a minus. So this is what we're working with now. So this is a minus K is equal to 0 to infinity of K, okay. And this is K plus R is equal to 0, okay. So we should have started more over. All right. Looks good. All right, so now what? Well, so now everything, the powers are good, right? The idea, just like the last time, the idea is to get the powers of X to be the same, right? So we do that, we do that trick, all right? Okay, so now the powers are the same. All right. The thing though is that this was starting at -1, right? This is starting at -1 and this is starting at 0. So I'm going to write out the first term here. All right. And then I'm going to have them all starting out at 0. And it turns out that this is going to give us an equation for R. All right. So let's see. So I'm going to write out the first term. So this is going to give me a 3. Right. Now, when I put 0 in here, when I put, excuse me, when I put -1 in here, this is going to be C0. Right. When I put -1 in here, it's going to give me, when I put -1 here, this is going to give me an R, right? Put -1 in here, this is going to give me a -1 plus R, right? And let's see, and then plus is going to be C0 here, right? This is going to give me a C0 here times, I'm going to put a -1 here, so this is just going to give me an R. Let's see, is that right? Let me make sure this is right. All right. And this is all times X to the minus, this would be X to the -1R. All right. We don't know what R is yet. Okay. Any questions so far? This is important now. So we have to expand this out, right? But now I have everything starting from 0, right? Okay. So, yes, someone have a question?
Yeah, for the last term that we wrote on the first line, if we replace n by k plus 1, why don't we have ck plus 1 x to the power n plus 1 plus r?
What?
Sorry, k plus 1 plus,
You talking about this?
no, the last one.
Yeah. No, we don't change that. We didn't change that. We already have what we need there,
Oh, okay.
right? We already have, we already have, just like the last time, we already have what we need there. We're not changing this, right? We're only changing the indices on this and this. This is what we want to go to. We want all of these to be the same, right? So we're not changing that,
Oh, I see.
okay?
Mhm.
You know, follow, yeah, okay. All right, so now everything here is equal to 0, so this has to equal 0. This has to equal 0. Okay, so all right, now it also turns out that C sub 0 is not equal to 0, right? So let's see. So I could rewrite this. I could factor out the C0. Let's see. I can write this as 3. Let's see, 3R minus. No, this would be 3R minus this times this. So this is going to be minus 3R, right? This time this is going to be minus 3R, then this time this is going to be a plus 3R squared plus R, right? Both of these are not equal to 0. Both of these can't be equal to 0. So that means that this has to be equal to 0, right? Remember, everything here is equal to 0. Term by term on this side of the equation, we have 0, right? There's no powers of x. Everything is 0. So the C sub 0, I factored out the C sub 0. That's not equal to 0. And this is not equal to 0. Okay. So that means that this has to be equal to 0, right? So this has to be equal to 0. So let's see. So what do we got here? We got another way of writing this is let's see. I can write this as minus 2R. Yeah, minus 2R plus 3R squared. That has to be equal to 0, right? I could factor the R out. Let's see, maybe different in my notes. Right? So this is telling me that R is equal to 0, right? R is equal to 0, and then minus 2 plus 3R is equal to 0. So this is 3R is equal to 2. So R is equal to 2 over 3. Hopefully that's what I got in my notes. Okay. So so now I got my two values of R. In this case, you don't always get two values of R. I'll talk more about this later. But the problems I'm going to give you, you'll have two values of R. But I will talk about different cases. All right. But once again, you're going to have a problem like this where well, you'll end up getting two values of R. But I'll show you what you could do. I'm not going to give you a problem, but I'll show you. I do want to explain to you that what do you do if you only get one value of R? All right. There's different conditions. I do want to talk about that, and I'll probably talk about that tomorrow. Where are we now? Okay. Yeah, finish this up. Okay. So we got these two values of R. All right. And the reason why we'll see later is that we call the larger value R1 and the smaller value R2. So we're going to call this 2, and we're going to call this 1. I do want to talk about conditions, which I'm not going to test you on. All right, but I will talk about the different conditions of why we call the larger value R1 and the smaller value R2. Okay. All right. So all right, so now we're able to determine R1 and R2, and this is called the initial equation. It has a name. I may not be. Let's see if I spell it right. That's what this equation is here. Okay. All right, now let's see if I got room. All right, so now, all right, so now I got this. So we worked on this and we got with R1 and R2. So now I can put everything under a common summation, right? I can put everything, I can write everything now as the summation, k is equal to 0 to infinity, right? Everything's going to be, it's going to be 3, and yeah, it's going to be 3, and then this is k. I'm just putting everything under the same summation. So that's the key thing with both of these problems, that first you got to get the powers the same, and then you got to get the summation the same, and then you put everything under the same summation, and then we can get the recursion relationship. Okay, this is going to be this is let me make sure I copied this right. I copied this right. And you know, we do have this over here. Okay, so let's see. Okay. All right. So let me I guess we'll get to finish this. Let's see here. Let me just check something here. Let me make sure you can see what I'm doing here. All right. So so this is what we have now. All right. So what we want to do now, what happened? All right. So so this here, right? Everything that's in the parentheses here has to be equal to 0, right? This whole thing is term by term, this is equal to 0, right? So let's see, what's the best way to do this? Okay, so I'm going to factor, I'm going to write this as k plus 1. And I'm going to write this as 3. We'll take a look at this. It's k plus 1. K plus r plus k plus r plus k plus 1 plus, that's r. All right. And then this is going to be minus. Okay, see what I did is all I did was I factored this out because I want to solve for this. Remember, we want to solve for the higher one, right? Okay, so I want to solve for the higher one. So now, so what do I get now? Let's see. Oh. All right, so I can bring this over to here, right? I think I did another. Okay, let's see. I'm going to rewrite this. This is times this. Now I'm going to factor this out. See, here I got a common, and here I got a common. All right. And then I got the 3. So I'm going to rewrite this. Rewrite it like this. There's more than one way of doing this. This would be 3. Put that over here. Okay. So yeah, I factored this out. Right? Factoring this out. Is this yeah. And then this is a 1. Yeah. So when I factor this out, you can get a 1 here. Right? So you get this. That looks right. Okay. So and then I could I wanted to write it like this just to make it. I can write this as 3k plus 3r plus 1 So see, I'm getting my recursion relationship. So now, okay, so what I did here is I divided both sides of the equation by this. So now I got this. And this is going to be true for k greater than or equal to 0, right? Because we're starting from 0. So let me just check if I got the right answer. Okay. Okay, good. All right, so now we got our recursion relationship. Okay, let me do all right. Everybody's with me? These problems are long, but they're not hard. All right, so now remember, now we have two values of r. R is equal to 0 and r is equal to 2/3, right? This is the 1 and this is the 2, right? So I put in r is equal to 0. How we doing on time? Okay, I put in r is equal to 0 here, and I get I put r is equal to 0 here, I'm going to get this. This is the easy one. This is going to be k plus 1. I put r is equal to 0. And then this is going to be 3k plus 1, right? That's r is equal to 0. Okay. Then I'm going to put in r is equal to 2/3. So I'm going to get one relationship. It turns out that's going to give me one series solution. Remember, we need two independent solutions. So this is going to give me one set of, it's going to give me one power series set. And this is going to give me another one. Okay. So, so now this one here, we're just going to put in the 2/3, right? That's all I'm doing here is I'm putting in the 2/3. Okay. And let's see. You factor 3 out of here. If I factor 3 out of here. Okay. Oh, I need to save some time. But when you do the algebra, let's see, when you factor 3 out of here, right? When you factor 3 out of here, this is become 3k, and then you're going to get a 3 here, right? Factor 3 out of here, and then this become 5. So when you factor this 1/3 out of here, right? You're going to get the 3k plus 5, and then here you take the 3 out of here, right? And then that 3 is going to cancel with this 3, and you end up getting k plus 1, right? And you take the 3 out of here, take the 3 out of here, right? This is okay. This is 3 here, right? This is the same as 3k plus 3, right? Right. This is the same as 3k plus 3 because this cancels with this. So does everyone see how I got from here to here? You take the 3 out of here, and you don't have to. You could actually leave it that way. But if I take the 3 out of here, then this becomes 3, right? Then this becomes a 3 here, and 2, so you get 3k plus 5. And then this here, this is 3k plus 3, right? This is 2 here, and this is 1. Factor the 3 out. I'm just making sure myself. Factor the 3 out. And so that 3 cancels with the 1/3 I cancel. Okay, so this is right. All right. So now we have two recursion relationships. Tons of fun, right? This is tons of fun. So now we got two recursion relationships. So now with the two recursion relationships, I could let's see. Let me So let's see. So let me, I'll write the recursion relationship. This isn't hard, it's just long, right? It's tedious, a little tedious. Okay, so this was the case for R2 is equal to 0. And then we got R1 is equal to 2/3. And that was what we got for there was this. Well, this is a K plus 1 here. Okay. All right. So let's see. So now, let's see. So let's see. So I can say now that I've put 0 in here. Now these start, both of these start with K is equal to 0. K greater than or equal to 0. So if I put 0 in here, C0, this is going to be 0, 0. So this is just going to be 1. I'm going to write it as 1 factorial. I'm going to write this. I know I'm going to get factorial with this. So I'm going to write this as 1 factorial times 1. And that's equal to C1. Then C2 is going to be equal to C1, right? And then this is going to be 2, right? When I put 1, this is going to be 2. Now when I put 1 in here, this is, when I put the 1 in here, right? This is going to be, yeah, this is 3K. So it's going to be 3, so this is going to be 4. So I'm going to write this now as C0, and then I'm going to write this as 2 factorial times 4. I know that when I have this in a recursion relationship and it keeps repeating, I'm going to get factorial. So that's why I want to do it that way. Okay, so C3 now is going to be C2, right? C2, and it'll be 3 times 7, right? Because when I put 2 in here, I'm going to 3, and this is going to be when I put 2 in here, I'm going to 6 plus 1, so that's 7. But now, once again, we're doing recursion here. So this is C3 is equal to C2 times this, but C2 is going to be C0, right? C0, then this is going to be 3 factorial, and then it's going to be 4 times 7. Right, 3 factorial. I actually should write this as 1, 2. Write this as 1 times 4. And then this is going to be 1 times 4 times 7. Right? I don't want to multiply it out. And then C4, I'll just do one more. C4 is going to be C3. And then this is going to be 4 times 10, right? It's going to be 4 times 10. And so this is going to be C0, right? And then this is going to be 4 factorial. And then this is going to be 1 times 4 times 7 times 10. Okay. So I got my C1, 2, 3, and 4. Okay. So now this one here, I'm also going to get, I mean, that C1 now is going to be C0. And when I put 0 in here, this is going to be 1. And then this is going to be 5, right? When I put, let's see, yeah, this is going to be 5. When I put 0 in here, so I'm going to get 1 times 5, right? Right? Put 0 in here, 1 times 5. So that's my C1. My C2 is going to be C1, right? And then this is going to be 2. And when I put 1 in here, this is going to be 3 plus 5, which is 8, right? So I can write this now as C0. And I'm going to write this as 2 factorial times 5 times 8, right? And then C3, let's see, C3 is going to be C2. On a test, just if you do the first 3, I'm happy. This will be 11. And there's gonna be C0, and then there's gonna be 3 factorial times 5 times 8 times 11. And then C4, I'll do one more. C3, and then this is gonna be 4, right? This is gonna be 4, and then this is gonna be times 14, right? This is, yeah, that's 9 times plus 5, yeah, it's 14. So then this is going to be C0, and then it's going to be 4 factorial times 5 times 8 times 11 times 14. Okay. All right, and it turns out if you'd spend the time, this is going to be n factorial when I go to the n, and then it's going to be 1 times 4. There's a pattern. That's why I did it this way. Up to up to 3n minus 2. So you can write this generally like this. If you put this in, you'll see. You don't necessarily need to. Yeah, get something like this. You don't need to be able to figure this out on the exam. Sometimes they're very difficult. Sometimes they're easy. And here now, for this one here, I'm getting Cn. I can write this as n factorial. And now this is going to be 5 times 8 times 11 up to 3n plus 2. So this is a general way of just writing these. Okay. Now, when we get something like this is going to give me one solution, and this is going to give me another solution, all right? Remember, when we have a second order differential equation, I need 2 linear independent solutions. So I need to relabel one of these, okay? So you need to understand that these are not the same, right? This is one solution, this is another solution. This is for one value of R, this is for another value of R. So I can call this B, I'll call this B. I can call this A and call this B, it doesn't matter. But, so let's see, which one did I do on my notes? Okay, so I renamed this one here as B. I just renamed this as B. We're almost done. Okay, so I'm just renaming this one as B. Okay, let's see. Okay, so so now that I renamed it as B, okay, let's see. Let me just take a look here. Let's see. I want to make sure. Okay. You can just see it. Okay. All right. So I have this and this, right? So this is getting, so these are the coefficients for my 2 solutions. Where are we? Okay, we're going to finish just in time. All right. So right now, this one here was R is equal to 0. Yeah, this one here was always equal to 0. Okay, so my Y1 now is going to be equal to the summation of B to the N, right? X to the N plus See, I can write that now as B0 x to the 0. Now, see, my R is 0 for this first one. Maybe I should do the second one. Summation of n equals 1 to infinity of b to the n x to the n. Well, maybe I looked at a step here. R is equal to 0 in this case, right? In other words, for this one here, for the b's, R is equal to 0. So this is actually n plus r, right? But since r is 0, I'm just writing it like this, right? So so this is one of my solutions, right? So I can write y1 as equal to b0 x0, which is just 1. I can write that as 1. And then the summation where n goes from 1 to infinity, and then I just put this in here. So this would be b0 this is 3. Okay, so this is one solution. All right. And see, you can factor out the b0 if you want, right? So another way of writing this. Now, on the exam, it'll be you won't have to do it in closed form like I'm doing it now. I think the problem I give you, well, you'll see what you have on the website. Okay. So another way of writing this is I can write this like this. I can write the b0, and then I can write this as 1, right? Because this is 1. And then this is right? So that's one of my solutions, right? That's all I did here was I factored out the b0. So that's just another way of writing it, right? And then the other solution, well, this I would write now like this. I'll call this Cn, right? Cn. Now, in this case here, it's n, right? It's before this was 0, right? The R was 0. Now the R is 2/3, right? So let's see. So we can write this as C0 x to the 2/3, right? Plus the summation, right? N is equal to 1 to infinity of Cn x to the n plus 2/3, right? I could write it like this, where I just took out, I started with n is equal to 0, right? This is n is equal to 0, but now I'm just starting it from 1. All right. So so let's see. So then we can write y2. I can write y2 as C0 x to the 2/3 plus the summation n is equal to 1 to infinity. And then I put in what my CNs are, right? Here's my CNs. My CNs are C0 n factorial 5 times 8 times 11, right? Dot, dot, dot. 2, 3n plus 2. And this is x, x to the n plus, all right. Well, let's see. Yeah, I could write it like that. Yeah, you could write it like another way to do it too is to factor out a 2/3. Oh, we could leave it like that. Or we could write it another way. I guess I have it written like this in my notes. This is x to the 2/3. And then I wrote this as 1, right? Bringing this through. And then this would just be x to the n. Because now this is times this, right? So this is another way of writing it. I'll do another problem like this. Where it's more like, let's see. So here's the problem I just did, right? The problem is in my notes. I guess it's time. The problem is in my notes. So this is the problem I just did. It's 4 pages long. Yeah, so this is the problem I just did. I'll do another problem that'll be maybe more like what you would get on the exam. Okay, there's another problem. So you should take a look at this problem here. Maybe tomorrow we'll go through this problem. Okay, the problem that you see here now. And then, so tomorrow, yeah, so this is another problem. Okay. All right. Tons of fun, huh? These aren't hard, am I right? They're not hard, they're just long, but they're not hard. Once you get the process down, it's one of these things where you got to practice. And once you get the process down, it's pretty straightforward. I found that that students, when they first see this, they go, "Oh my God!" But then they always manage to get it right on the exam. Right? This is the type of problem that they normally get correct. In the past, the students have gotten this correct. So, okay, so tomorrow we'll do another method of Fabina's problem, but maybe I'll let you try it. Start it first. And okay, so that's it for today. I hope I'll be happy to answer any questions, but I'm not going to answer any questions on the exam. Okay, if you have questions on the exam, I hope you're making good progress on the exam. Okay, have a great day. I know I kept you a minute over today.
Thank you, Professor. You have a great day.
Okay.
Thank